Good afternoon. Today in a week, there's the final, is that right? We'll have 48 questions. Of these 48, I think 16 are from the fourth section, the one since the last midterm, and the rest of them is all over the place, okay? Goes from 1 to the end. No, goes from 1 to 3. Midterm 1 to 3. Okay, thank you for coming. It's voluntarily. I'm here also voluntarily. And so let's have a little bit fun today. And I'm going to continue with the review that I did. I finished the fourth part, and then I will go to the first part and second part and third. Let's see how far we come, okay? And let's play with this. But first, we're going to do also an experiment. And I'm pretty excited about this, and I hope I can excite you about this too. You know, redox reactions have two partners. There's not one without the other, okay? Reduction and oxidation. So one partner furnishes the electrons, and the other one takes the electrons. The one furnishing the electrons, it leaves the electrons leaving that partner, and that means it's being oxidized. With this, the oxidation number of that guy increases due to the loss of the electrons. And now there's these extra electrons, and they are accepted by the one that is being reduced. The electrons will be accepted by that by that second half cell, or by that compound in the second half cell. And so with this, the oxidation state or the oxidation number goes down. Okay, it's being reduced. So, and you can make, if you separate those two half cells, one that is being oxidized and one that's being reduced, you can separate those with each other, and can you get the energy out of this? Because there's a potential. There's a difference in free energy, and there's a potential difference between those. So this is two half cells. This is zinc 2 plus in contact with zinc metal, rod. There's zinc 2 plus and SO4 2 minus, 1 molar. And this is copper 2 plus in contact with a copper metal piece, and there's copper 2 plus and sulfate 2 minus. So this is electroneutral and this is electroneutral, okay? Now, the reduction happens at the cathode, red cat, okay? The red cat doesn't exist anymore. I had to bury him yesterday. We found him dead in the neighbor's yard. That's not a joke, okay? And anyhow, so I buried him yesterday. But I will still show him in memory of him, okay? I will still show him red cat. Now you will even remember. And so he must have died of a heart attack or something, you know. And anyhow, so you knew him. Okay, so the reduction is the cathode. Now, when the reduction happens, is this the one which has the higher potential or the lower potential? Who is for higher? Higher, okay? That's the one more positive. That's where the reduction happens, okay? And everything's below that one gets oxidized, right? So zinc must be below, and it gets oxidized. Zinc goes into solution. So the zinc metal gets oxidized. That means the zinc metal goes into solution as zinc 2 plus, leaves 2 electrons behind. These 2 electrons can wander across here from left to right, from cell 1 to cell 2, from left to right, okay? And then they come down here, and now that copper 2 plus, which wants to be reduced, sees these 2 electrodes and says, okay, I'm going to take these 2 electrons and they come out as copper metal. All right. So with this, we have a potential, but the potential is only if we have a charge balance, okay? And we have a salt bridge, and this is usually potassium nitrate, K plus NO3 minus. It's put in a solid form in agar that it doesn't totally diffuse out. And so what happens? If this zinc goes in solution, I'm making more and more positive charges, all right? But the sulfate in the solution did not change, all right? With this, I have an excess of positive charge. So here I have potassium and nitrate in there. So in order to compensate that positive charge, the nitrate will diffuse in here and make this again electroneutral. And here I have the copper coming out of solution. That means I have an excess of what kind of charge? Negative charge. The negative charge comes from what? from the sulfate ion that's left behind. It's not balanced anymore, copper sulfate. It's not balanced anymore. And so what will have to come in here, what has to diffuse in here to make the charge balance again? So say again? So the potassium, the K plus, diffuses in here to neutralize the electric charge of the sulfate, all right? So I want to show you this experiment here. And I've shown it to you many times. I scaled it up now a little bit. And so what you look at this here, I have a big and a small salt bridge. Let's use the smaller one here. So we read 1.07, 1.08 volts. And now I have shown to you when we used 4 or 5 people that we could be a human salt bridge, okay? So one person sticks the hand in here, or the finger in here, or 2 fingers would be better, in here, and the other one in here, and there will be, maybe the salt bridge is not working. That's not good. We need the humans to do it. Yeah, there it is. It's a little dilute now. 1.05, okay? So it's about 1.1 if we with rounding. All right. So, of course, if I have a very large number of people in there, I have resistance. Each of you have resistance. You're in a resistor. With this, you have a voltage drop. So we will not see 1.05 volt if I have 100 people standing here, all right? And I determined from this morning that the voltage drop, it doesn't matter. We will see, okay? So what I want you to do is, I want you to stand in rows, this row starting with this row. First of all, okay, come down here, form a line from here to here, till you get in that row here, okay? In that row, yeah? So some of you come down, and then you go in that row. The other ones will stand here. So you will be one electrode. Who wants to be an electrode? So, okay, you stand here, and you stand here. Come on here, come on here. Come. All right? So all of you, let's get stand. So you stand up, and I want to form a row up here to connect always here, okay? When this row is full, then we connect here, and then we connect here, all right? So come on down. Come on in, I need more people to connect. Connect, and then now I need this row full here. When you are to that row, a little bit more, now you go in this row, please. Now, start, please. Start, okay? And you go into the second row from here. You start here, you please. You go all the way over there. Okay? Come on, go in this row here. All the ones of you, go in this row here. In that row. Come on. Go. Keep going. Come on, guys. I don't have forever. Did you get your hands wet? Yes. Yeah. Okay, good. Did you get your hands wet? Okay, good. This row, okay. All right. Right, closer. You need to go all the way over there. We need to connect there. Keep going. Keep moving. Okay, keep moving. Now you go in this row. Keep going over there. You guys, the second row. Keep going all the way to there. Keep going. All the way to the end, please. Okay.
Can you guys block that projector, please?
Okay. So, are you there? 1 second. Keep all the way over there that you can reach with these guys. Okay. All right. Keep going. All right. So now let's fill the next row. Keep going. All right. I need 3 more people here. 3 more people here, please. 3 more people here. Standing here. 1 here, 1 here, 1 there. Okay. Keep going in this row, please. All right. Good. All right. So what we're going to do is we're going to connect first from here. You are the connector with him here. Okay. And You are connecting. You're connecting here, exactly. So you're connecting here. We leave that out here for now, yeah? And then we go around one more row and add the next row. So, can you step on the side a little bit? Step on the side. So you see this up there? Can you hold hands now? Just the ones which are connected. So I have the connection through this row here, all the way through here, all the way through here, all the way through here. So I take the salt bridge out. Now, you really got to have good contact. Now, put your 2 fingers in there. Put your 2 fingers in there. Somebody is not connected. Keep connecting. Hold hands. Are you really holding hands? Yeah, there you go. Okay, 1.03. 1.03. We had keep holding hands. Don't interrupt it. You got to keep holding hands. Okay, 1.04. So let's stop. That's cool. Now, you're going to go, and you're going to connect with those guys here now. You're going to connect with those guys. You connect with those guys, okay? And you're going to have to, some of these guys, some half of that row, this row here, go over to the other row a little bit from the end. From the end, go some in there. All right. Keep going. Some more. I need some more. You 2 guys in the back there. Keep going. Keep going till you meet, really. 2 more up there. 2 or 3 more up there. Go in the next row. Left, left, up. Yes, you lady. Ma'am. Okay. All right. Stop. One more. Stop. Okay. So now you got to be able to connect with these guys below. Let's see, we connect here. So we are connected from, no, you are out, okay? We are connected here, you go here, you go there. And so you now got to connect now. Let me go in there. Let's see. You got to connect. So we got to make a connection here at one point, okay? You guys got to connect with them here. Here. Got it. Some more up here. All right? So you all have wet hands? Okay. You got to really hold them. Good contact, yeah? Make sure that your hands are wet. Your hands are wet. Okay. Now, you had this all the time in there? Yeah. Okay. Put it back in. Now. Everybody connected? Come on, connect. Everybody connected. Do we have a closed circuit? No. That's not a closed circuit. There's somebody not connected. Yeah, 0.95. Very good. Let me get in there too. Okay. I go in here. All right. What does it read? 0.96. Yes, we did it! It works. It works. So I need to count then. I do the iClicker count, and then I do the hand count for those who don't have clicker. It works. It works. No, it is only because each of you is a resistor. And with this, the voltage drops a little bit. R is U divided by I, okay? And so if I have too many, I could up the voltage a little bit, take another cell. But we will. That was cool. Thank you. It works. So you wash your hands here. Did you wash your hands? Did you wash your hands on here? Here. Can you turn on the water in the back, please? Wow, it works. Yeah. Okay, it works. Good. That was worth the try. So what I know now, so why don't we take an iClicker count? It increased. Yeah. I'm not very much of a resistant, obviously. Okay, clicking in that I can count you. who don't have eye clickers, and who have eye clickers, they raise their hand when I ask them, okay? Who don't have eye clickers. Come on, everybody with eye clickers, click in. All right? Everybody click in. I want to have the count. Everybody clicked with eye clickers? Everybody in? 85, 87. So raise the hand who doesn't have an eye clicker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I had you guys. 20, 21, 22. That's it. 22 plus 90. 22 plus 90 is 112. Okay? 112. Not bad. I would like to see 400 though. All right? Huh? It works. So it's not a myth. How you call that show where these guys at Alameda are Mythbuster, okay? That was not a myth. It works. All right? In the morning, we're only 48. Okay. Yeah. Okay. We don't want to get eye clicker. We want to just go on, okay? All right, now let's go on with our review. Let's be even more serious. But this was serious stuff, okay? It was not a joke, okay? So you understand now how this works. You know which one is the right one is the cathode, the red cat here, okay? That's the anode. It flows from here to here. Ka-ching, 5 points, okay? All right, so we then talked about standard reduction potentials. Oh, I lost them. Okay, standard reduction potentials are listed from positive to negative potential. Here they are, okay? Oxidizers oxidize all material with lower potential. So everything positive is an oxidizer, like gold could oxidize everything below, all right? So oxidizers oxidize all materials with a lower potential. So the only one that could reduce gold would be permanganate. See that? Permanganate could reduce gold. It becomes oxidized, and gold is below. It goes in this direction. Gold would be oxidized by permanganate. Standard reduction potentials are useful in balancing complex redox equation. You look for the pair of the two, and then you put it in, and you make sure that the right amount of electrons are exchanged. You have to multiply it, and then you make sure that one has it on the left side and the other has on the right side, because when you add it up, they need to go away. Okay, they need to cancel each other, and I have shown you this the last time. So galvanic cells with positive standard cell potential react spontaneously. Why is that? Because delta G is minus N times F times delta E, all right? And when delta G is negative, then you have a spontaneous reaction. There it is. Which of the following will oxidize nickel but not silver? Everybody got to have this right now. Which of the following will oxidize nickel but not silver? So obviously, if nickel gets oxidized, that means the reaction for nickel goes in this way. So everybody above will do that, all right? But silver is also above. So if this gets oxidized, that would be oxidizing silver, anything above silver. Isn't that right? Why don't you think about this and give me your answer? There's no need to think about it. You know it. I give you 1 minute. Everything above will oxidize nickel. And it has to be in an oxidized form, the one above, because it's getting reduced. So nickel has to go in this way, from this direction, and the others one have to go in that direction in order for the nickel to go in that direction. Okay? Yes. Good. You get it. That's very good. So we have 73, 90. We got 3 more. 3 people didn't go into that. We had 90, didn't it? No. Never mind. They found mysteriously their eye clickers. Okay, so what happens here? Which of the following will oxidize nickel? So that's what we want. We want to go in this direction. Nickel gets oxidized to nickel 2 plus 2 electrons. Okay? Who rips these electrons off from the nickel? Everybody above. All right? So copper 2 plus would take 2 electrons and make copper 0. But copper 0 doesn't do anything. It's already in the reduced form. Okay? This is out. Now, this one, nickel, whereas bromine, of course, bromine rips off these 2 electrons of this here and makes bromide ions. This is 1.06 volts. But silver is below. It also will oxidize silver. The silver will get oxidized. So the only one, so this is out, okay? This must be the only one then, because it's above nickel. It's H3O plus, takes 2 electrons and makes hydrogen gas. That's the standard hydrogen electrode. When hydrogen electrode will do that, and with this the answer is H3O plus, and everybody understands that. That's very good. They understand the Latimer potentials. Good. Now then we talked about radioactivity, and I know what happened here with my... I fixed it and I lost it, okay? Never mind. Radioactivity is a nuclear phenomenon. So that happens in the nucleus. Everybody above bismuth is radioactive. Any element above bismuth is radioactive because the neutron to proton ratio is out of whack, all right? Completely out of whack, all right? And it will never be at a stable ratio. Of course, the half-lives are very long. Some of them are millions of years or billions of years. So for us, if we use it, it's relatively stable, okay? Some of them have short half-lives. So the stability of the nucleus depends on the neutron to proton ratio, and the stable nuclei have a ratio from 1 to 1.5, and I show you all this, okay? From 1 to 1.5, depending on the atomic number. So if a nucleus doesn't have that ratio, somewhere between 1 and 1.5, it wants unstable, and it wants to reach that ratio, okay? So if it has too many protons, for example, it says, okay, I have too many protons. I convert one of my nuclear proton to a neutron. And what else? I had a proton, that's positive, and I have a neutron, this is neutral. So I need to balance the charge. What would be that? Protons, too many protons. Neutron plus a beta plus particle, an electron with a positive charge, a positron. Now and with this, it decays with beta plus, and so the proton goes to the neutron and a positive charge. And now what happens to the parent nuclide? The parent nuclide will be 1 lower, the daughter nuclide will be 1 lower in atomic number, because that proton converted to a neutron, okay? But the number of nucleons will be the same, because the proton is a nucleon, and the neutron is a nucleon. So the number up there on the A number will be the same. The Z number will change. So if I have, what did I have? If I have a neutron, too many neutrons, what does the neutron, it wants to be a proton, isn't it, in order to reach that ratio. So the neutron converts itself into a proton. With this, the atomic number goes up into a proton, and what else? And an electron, a nuclear electron. That's called the beta minus, all right? So if a neutron goes in a proton, the atomic number goes up 1. But the neutron and the proton are both nucleons, so the A on the top stays the same, all right? C changes, but A stays the same. We're going to go through this. Above very heavy nuclides, they can stabilize by this decay, by alpha decay, by beta decay, beta plus or beta minus decay. By alpha, they spit out a helium nucleus. Helium is 4-2. It's atomic number 2, 4 nucleons. It just spits it out, and it's leisurely said, it ejects it, okay? It ejects it, and and with this, your number goes down, your proton number goes down by 2, and your nucleon number goes down by 4. All right? So, and there's one thing is, if you have beta plus decay, that means you have a positive electron with a positive charge, a beta plus particle, is not stable. It immediately grabs electrons are everywhere, grabs an electron and converts the two masses. They essentially have the same mass, the positron and the electron have the same mass, converts it to 2 photons, okay? Conversion of mass to energy, right, by Mr. Einstein, or Professor Einstein. So let's see. So by increasing nucleon number, the nucleons, these are the particles in the nucleon, the protons and the photons, they are bound stronger. If I have more nucleons, they are bound stronger, and if they're in the right ratio, then they're even bound very, very strong. So, and with this, if you make from lighter nuclides, you make something heavier, they bound stronger, so they release energy, and I will show you all this here right now. Okay, and you can use this effect in nuclear energy. Now this is the number of neutrons, this is the number of protons. We see this would be a 1-to-1 ratio. It doesn't happen, okay? Number of protons would be 1, number of protons would be 1, number of neutrons would be 1. But this is the real ratio. All along this here, you have stable nuclides. They are stable. There's no radioactive decay. So this is called the valley of stability. Valley of stability, okay? The green valley. All right, and that's where they're trying to get. If you have this here, for example, let's say we have one with 40 protons and let's say 50 neutrons. That means we have too many neutrons, okay? So now a neutron gives what? Converts into a proton and an electron. So if the neutron goes into a proton, we move one over here, okay? And the electron gets ejected. And this does it several times, ejects more and more electrons till it's here on that line. Then it's stable, okay? Now if you have, so that would be the electron that's ejected, it comes out of the nucleus. Now, if you have beta plus decay, what do we have? Do we have too many protons or too many neutrons? Protons. So let's see, we are here, but that's 50 protons and 50 neutrons. We would be here, okay? So now I want to convert a proton to a neutron, all right? So I move over one here and eject a beta plus particle, yeah? Proton to a neutron. So if I do that again, I move over again, all right? Till I'm on the line here. Not till the nucleus is on the line, all right? I don't decay at all. Actually, I do decay. We all decay pretty badly, actually, but that's a different story. It's called aging. So you see that beta plus, okay, and these are the different decays. Now, this is the systematics of the decay. You eject out of the nucleus an alpha particle, has the mass of 2, so you subtract 90 minus 2 must be 90. And then it has 4 nucleons, that is the protons and neutrons, is 38 minus 4 must be 34. So if you don't have this here, you look up what is 90. What is element number 90? That's thorium. That means that plutonium-238, element number 92, alpha decays into thorium-234. All right? Beta minus decay, we said the neutron gets in a proton plus an electron, and the electron gets ejected. So the neutron, so we have 53 protons here, but one nuclear neutron converts in a proton, that gives 54, okay? And since the protons and nucleons are both, protons and neutrons are both nucleons, the number 131 is the same, right? With this you have the beta minus decay, beta plus decay, you have the proton converts in a neutron plus a beta plus, okay? So the proton gets a neutron, that's 11. So one proton is converted, that is then 10, but the number of nucleons stay the same, and this we have beta plus decay. And when you have beta plus decay, that means positron decay, you will have always annihilation of the 2 electrons to give 2 gamma quanta, yeah? 2 photons. There it is. So you can calculate the mass. The mass of an electron is 5.49 times 10 to minus 4 atomic mass units. We said an atomic mass unit is about 2 times 10 to minus 24 grams. So if you multiply this in here, then you have it in grams, the change in mass, okay? This is the rest mass, or the mass of two electrons, okay? The positron and the negatron have the same mass, all right? So this is the delta M. This is the change in mass, so that's delta M. Now you need to multiply it with C squared. C squared is, in energy units, is 931 mega electrons volt per AMU. So you multiply that mass that you calculated here in grams with this here, or actually you don't do the grams, you just make the AMU. They will cancel here. You multiply this with 931. What you get then? You get 1.02 times 10 to the 6 electron volts, or 1.02 mega electron volts, right? Now we want to know how many joule is that. How many joule? You say 1 mega electron volt is 1.6 times 10 to the minus 13 joule, and you have, so that is 1.6 times 10 to the minus 13, so you have to put this in here, and with this you get 10 to the 11 joule per mole. If you take a whole mole of this, you get 10 to 11 joules per mole, and this is a tremendous amount of energy. Tremendous amount of energy. If you compare this with the forming of 1 mole of chemical bonds, it's about 100,000 joules per mole, okay? All right, so this is annihilation, emission, annihilation decay, positron decay, and so this is what I said earlier, the binding energy per nucleon. You know the nucleon, you have any idea how big the nucleus is compared to the whole atom? So it's about 10 to minus 15 meters compared to the 10 to minus 10 meters would be the whole atom. Okay, it's 5 orders of magnitude. I remember I had a coin here, and that coin was a quarter, and I said the 1 s orbital electrons would sit about there at the Berkeley BART station, okay? These are these 5 orders of magnitude compared to that coin. And so you can, and this is the binding energy per nucleus. When they bind, they release energy. And this is what they release. To make a hydrogen, it's the release of about 1 MeV per nucleon, okay? And if I have hydrogen and heavy hydrogen, if I fuse those together, then I get helium, helium-3, not helium-4, helium-3. And helium-3 has nearly twice the, or 1.5 times the binding energy, no, more than twice the binding energy of these guys here. So when they bind together, this binds with this here, it releases a tremendous amount of energy, right? And this energy is what happens in the sun, on the surface of the sun. This is one of such fusion reactions. There are several other fusion reactions that happen, but they're all with very light nuclei. Now, if you could fuse, for example, iron with some lighter nuclides, you would make a very stable nucleus, but it would have a binding energy of close to 8.5 mega electron volts per nucleon. So you have to multiply this by the number of nucleons in order to get there. Don't worry, it's not going to be in the test, all right? So the other way is, and that stops, the highest binding energy is iron. That's the most stable element, actually, iron 56, okay? So it goes down then, the binding energy again. Now, if we could split those here into 2 smaller ones, and the 2 smaller ones, when they form, they release energy, then this would be one smaller one, or the other smaller one would be here maybe. That would be barium, and this would be krypton. It's higher than this here. That means you release energy. And you use this, you have the uranium-235, it picks up a neutron, and it explodes, and then it reforms itself to a lighter nucleus and a heavier nucleus. There's a combination of all those to make the same mass number, essentially. And it releases through 3 neutrons, okay? And these neutrons can react here again with this, and with this again, and with this you have a chain reaction. And in a reactor, you very well control this. There's not going to be a chain reaction. So with this now, you release, when they reform, you release quite a bit of energy, 200 MeV per fission, actually. mega electron volt per fission. You can calculate how much this in joule is. I do this another time. Okay, let's go to lecture 1. Chemical reactions always, and we go as long as we can go, okay? I think I will give you quite a few pointers in this. And chemical reactions always occur in stoichiometric ratios. Atomic masses are weighted averages of the masses of the natural isotope of an element. That's why they are fractional numbers up there, okay, on the periodic table. The structure and the size of the nucleus and the atom, we talked about this. I just talked about the size of the nucleus and the atom. So we also talked about obtaining empirical formulas from experimental data. That was mass spectrometry. This was combustion, either combustion of hydrocarbons, where we make CO2 and water. And by the amount of CO2 and water that you have, you can calculate what is the empirical formula. And if you have the molar mass of that here, then you can get the molecular formula of this. And you need to remember something like this, not necessarily this. We ionize our sample in a mass spectrometer, and that means we rip off some electrons, and then we accelerate it here with a negative charge because this becomes positive, and then we deflect it in a magnetic field, and the slower they are, the less deflected they are, or if they have the same velocity, the larger ones get less deflected than the smaller ones. And this would be now a larger one, and this would be less deflected. And this is called a mass spectrum, and we have then talked about a mass spectra. And this was mass number 1, this would be hydrogen, and mass number 2 would be 2 hydrogens here, or a heavy hydrogen, so the hydrogen molecule. What other masses did we have? This mass number 3 could be helium-3, or hydrogen, and the heavy hydrogen forming a gas. What was that here? 12, carbon, 12, and there was carbon 13, the radioactive carbon. And then we had what is 13, 14, 15, 16. What is that? Oxygen. And then we had 18. What could that be? Water or heavy oxygen. All right? Now then we had 32. That could be an oxygen molecule. 34 could be oxygen molecule made out of oxygen 16 and oxygen 18. Of course, there are many, many combinations. I'm just showing you the principle. Or it could be, that would be 36, would be a molecule of oxygen made out of heavy oxygen. All right? Now, what's important is CO2. C is 12 and O is 16 is 28, but we have 2 O's here. 28 plus 16 is what? 44. Mass 44 is carbon 12, oxygen 16, CO2. 45 would be, for example, would be carbon 13, oxygen 16, O2, and so on. And so you can get, remember we did a chem quiz where you had to sort of assign some of these things, and I think that's something might be worth reviewing. And so then we talked about radiation and light, okay? Light, we know, behaves as a wave, but it also can behave as a particle. And radiation is light, essentially. Some of it we can see, that's the visible. Most of it we cannot see, and because the visible spectrum is only, the visible light is only a small part of the spectrum of electromagnetic radiation. Remember, it went from very high frequencies to very low frequencies, okay, or long wavelengths. So you knew when you have monochromatic light that it can interfere with it. Monochromatic means lights of one wavelength, one particular wavelength. Doesn't matter which wavelength, but it's got to be visible for us to see it interfering. And there can be constructive and destructive interferences. And matter can absorb and emit radiation light. We see this, what was that effect we had, the photo effect, where we can sort of shine light on a metal and it ejects an electron if it has the right energy. Right energy means not more, not intensity, means the right color, the right frequency, or wavelengths. Right? So this was the diffraction and interference pattern, okay? So this could be an electron, it behaves as a wave. It could be a light particle, monochromatic light particle. See that? That would be a photon, okay? It can also act as a wave. And so, it has to have one energy, of course, And so you have these constructive and destructive interference. And if you project this, for example, on a screen, you see bright spots and dark spots, bright spots and dark spots. So the bright spots are what kind of interference? Constructive interference. Where is the interference, the constructive interference, the highest? That would be here, wouldn't it be? That would be the brightest spot. Where would be the darkest visible spot? That would be out here, okay? Because the intensity, this is the measure for the intensity, the amplitude, the measure of it goes down. Now, what would it be dark or bright here? Here too, here too, here too. What would it be? Bright, bright, brighter, brightest, okay? Okay, good, you know that. So as I said, light can also behave as a particle. And now we have this dualism between light as a wave and light as a particle. Is it a wave? Is it a particle? What is it? Okay? And so these guys, the guy de Broglie unifies this dualism between light as a wave and a particle. A particle can have momentum. P equals m times v. And a wave can have wavelengths. And you can couple those. That would be the wavelengths. We say lambda, and this would be the particle with momentum. And for the wave, if you know the wavelengths, you can calculate the momentum. If you know the momentum, you can calculate the wavelengths. This is Planck's constant here, which will be given to you if you have to do this in case. So now, there's this duality, and this is how this is rectified now. It can be a wave, and it can be a particle. Okay, electrons with no can be, yeah, we have that. They form an interference pattern. The same can happen with electrons. I just said it again. And the magnitude of the de Broglie wavelength tells us if we are dealing with a quantum particle. What is a quantum particle? A quantum particle is a truck. My bottle here, my beloved coffee? No? So what is a quantum particle? Something that has a wavelength that makes sense. Okay, a wavelength that is within the dimension about a factor of 100 of the dimension of the particle itself, right? That's a rule of thumb. And so, remember when I had this rope here? The rope, what did I want to show you with that rope? That electrons can behave as standing waves, okay? And they can have, it depends on the frequency, or the wavelength and the frequency, if they are in low energy state, higher energy state, even higher energy state, higher energy state. So the ground state, what was the lowest waveform for the ground state? Was the electron in the ground state, does it have an energy of 0? No, exactly. Doesn't have an energy of 0. What's the ground state? The lowest energy of it's right here. It's half a wavelength, okay? Now, what would be the second one? Would be the second excited state, would be n equals 2, level 2. Has one node here. This has n equals 3, has 2 nodes here. No, 3 nodes. Where's the third one? Yeah, 1, 2, 3, okay? And which one would have the highest energy? Okay, so the one that have the most nodes have the highest energy. Somebody might ask you, what different nodes do we know when we talk about electrons? Yeah, what's radial and what? Radial and angular nodes, okay? This is constantly applies to all the nodes. If you have, of course, more angular nodes, you have higher orbitals, okay? They will be in higher energy levels, all right? Good. So now, this becomes, what makes sense for a quantum particle? A baseball, if you calculate the wavelengths of a baseball, you get something 6 times 10 to minus 26. That's such a tiny wavelength. No, it's not even tiny. It's so unexpressible small, all right? So this is not a quantum particle. A golf ball probably is also not a quantum particle. But a sodium atom at 80 K with this velocity has a wavelength of 0.06 nanometers. So we know that the atom, we say about 1 nanometer, okay, the radius of it. So this is within the reach of it, okay? This is a quantum particle. An electron is even more a quantum particle, and the photon even more. So the de Broglie wavelength goes up as they become real quantum particles, all right? So you go from very small and nonsense to something which makes sense. And this makes sense because we know this is in the realm of the size of the sodium atom. Okay? So we then talked about electronic configuration and the Aufbau principle. So you know all this, the electrons occupy orbitals as to minimize the energy of the atom, and lower orbitals fill first. And then you have Hund's rule. When you're filling the same energy type orbitals, the electrons fill them singly first and then with parallel spins. We did this here till the cows came home, all right? And so you need to know this probably. And then I'm behind here, okay? I'm about a couple of lessons behind. No, 11 is here, okay? Now, we then talked about orbital blocks in the periodic table. We talked about homologous element in the periodic group exhibit often similar chemical behavior. Why is that? So that's the group here. That's a group. That's the period from left to right. And from top to bottom is the group. Why would they exhibit similar behavior? The binding happens with the outermost electrons in the outermost orbitals, okay? And do they have the same electronic configuration, just at the different quantum level and the different orbital? Yes, they do. Okay, you get this? Because the binding is done with the outermost orbital electrons. And they have all the same configuration. Nevertheless, they are this is in a higher level. This is in a higher level than this one. This is in the next higher level because this is in the first period, second period, third period, fourth period, fifth period, sixth period, seventh period. Okay? All right. Now, what do we have? Ionization energy and electron affinity. I will talk about this. Atomic radii increase within a group. Atomic radii increase within a group. They're getting bigger, but they decrease within a period from left to right because you're adding more nuclear charge. It pulls in the electrons stronger. So that was the radius decreases. And electronegativity, and I come to this. So ionization energy. What is the ionization energy? Is when I want to take off an electron, or I need to take off an electron, so I make an ion out of a neutral atom and an electron. Would I need energy for that? Ionization energy, is that something that I have to put in, or something I get out by freely from the atom? So I have to put in, I have to rip off that electron. I have to take away that electron. I need energy to get it away from the because it's bound to the nucleus, to get it away from the atom, from the neutral atom. So, and the opposite is if I have some electron affinity molecules or atoms who are electroaffine, that means they want electrons. And they take an electron and incorporate it, and then they become, this is a cation and this is an anion. They become negatively charged. What does that mean? Is this a process where energy is released, or is this a process you need to bring energy to the system? Energy is released, exactly. So binding, the electrode binds. Binding is always energy released. Delta E or delta H is negative, all right? So here I gave you then the ionization energies. They're all positive, and the electron affinities are negative, all right? And then we talked about successive ionization. So the first electron is relatively easy to remove. But now you have one less electron, but you have the same nuclear charge, same positive charge. So that hangs on much tighter to the remaining electrons. So it's much more difficult to remove a second one, and becomes even more difficult to remove a third one and to remove a fourth one. This is successive ionization. So the first one takes only 580 kilojoules per mole, and then increases dramatically. So the last one is very, very difficult to remove. Ka-ching. Okay, now electronegativity is, what's the most electropositive element? Francium, okay? Francium, after the beautiful country France. And what's the most electronegative element? Fluorine, okay? Very good. And so if you have done if the difference between those two when they bind with each other has a certain number, you have ionic or partly ionic or homeopolar binding or covalent binding. I would wait if I would be you. The valence shell electron pair, I'll be done in a couple of minutes, 1 or 2 minutes. The valence shell electron pair repulsion model can be used to predict molecular shapes and geometry. So now we went from the Lewis model suddenly where we could predict some shapes of compounds, all right? So the VSBR, so we determined a steric number, and what was the steric number? Who can tell me what the steric number, how did I get to the steric number? Huh? Number of bonds? Plus the number, plus lone pairs, exactly, that's the steric number. Lone pairs are positioned to minimize the electron repulsion. So you had steric number 2 was linear. I would review this if I would be you. Trigonal planar, tetrahedral, these are the bond angles. Of course, they can be compressed if you have a free pair here or 2 free pairs here. And so now, very carefully, bonding and anti-bonding molecular orbitals are formed from linear combination of atomic orbitals. Now, we position the atomic orbitals so that we can do the bonding. And we use MOs are filled with electrons similar to atomic orbitals. Stability of MOs depends on the bond order. Okay, so you have two, what is that, for example? That's an S, 2 S's here, okay? They bond to a sigma bonding and 1 sigma anti-bonding, right? So you cannot lose electrons. This is how this would work here. You remember that, right? What's the bond order here? 0, excellent, good. So the valence bond theory uses hybridized atomic orbitals overlap either with hybridized or non-hybridized atomic orbitals to form covalent bonds, okay? The valence bond theory, we hybridize our atomic orbitals at that atom, and then we start binding with the other atoms. Depending on the overlapping orbital, sigma and pi bonds can be formed. And we use the VSBR geometry to determine the hybridization of the atomic orbitals. Now, this was the hybrid orbitals, 1s and 1p. This is 1s and 1p. How many orbitals do you need? You need 2 orbitals, okay? This is 2 sp orbitals. Then you have sp2, sp3. You don't have sp4, but you use then d orbitalization. And then you have these hybrid orbitals, and I talked about them. dsp3 or sp3d, okay? Now there's an example is iodine trifluoride. Iodine obviously has enough electrons to do this hybridization, and phosphorus has enough electrons to do that hybridization. You hybridize the D, S, and 3 Ps to get this kind of configuration. That's 90 and 120 degrees. Now, steric number 6 would be what? Would be a D2. You have 2 d orbitals, 1 s, and 3 Ps. So everything is 90 degrees here. And this would be sulfur hexafluoride. So the sulfur would hybridize like this, and each of them would bind with 1 fluoride ion. And this is xenon tetrafluoride. This is planar, okay? And this has 2 lone pairs. So that's why it's planar. And what's the bond angle here? 9 degrees. Ka-ching. Okay, good luck. All right, thank you for coming, and I will teach on Friday only at 1 o'clock, and I will talk about the Berkeley and the actinides, something you can be proud about, okay? Friday, 1 o'clock. Otherwise, I don't see you anymore.